Hi, hello, 大家好, and vanakkam. My name is Yo Gin Yo.
My name is Hafizan Hafi.
My name is Aisha. My name is Izri.
My name is Madani.
And we are the members of Group 3.
For the first task, we are required to select the best reactor and also the type of catalyst used. The type of reactor selected is packed bed reactor, PBR, and the catalyst used is palladium with activated carbon. Packed bed reactor is the most suitable reactor for this process due to the use of a heterogeneous catalyst, a solid catalyst. PDC was chosen as a catalyst because it enhances the selectivity of the desired reaction. Moreover, this reaction is classified as a continuous flow reaction where the inlet and outlet streams are flowing continuously and with the presence of a catalyst bed. That's why PBR is the best reactor to be used in this case.
Will uh, describe to you about the task 2. Yeah, that's the description on how reactor separator work. First of all, the feed will go to the hydrogenation reactor. In this hydrogenation reactor, we choose for PBR because in this reaction then there's need some catalyst to for the reaction. In this reaction, the impurities of the crude TA will react with hydrogen to produce p-toluic acid. So the impurities in the TA will be decreases and it will become more purified. Next is evaporator. In the evaporator, the product from the hydrogenation reactor will be evaporated to reduce some amount of water. The reason why to reduce some amount of water because to increase the yield of TA. The steam stream in the evaporator will be added so that the changing of energy for the water in the feed can be vaporized. Next is crystallizer. In the crystallizer, the crude terephthalic acid filter cake will be formed and it will be dissolved in a selective crystallization solvent at an elevated temperature to form a solution. Then the purified terephthalic acid will be crystallized from the solution in the crystallization solvent by reducing the temperature of the solution and separating the crystallized purified terephthalic acid from the solution. And as for the crystallizer, we choose the cooling crystallizer.
We'll talk about task 3, which is strategy to maximize the selectivity and the yield of purified TA and minimize the side reaction. Based on the chemical reaction, the desired reaction, which is production of HMBA, have an activation energy of 29.65 kJ per mole, while the undesired reaction, the production of benzoic acid, which is 4-CBA decarbonylation, have higher activation energy, which is 74.32 kJ per mole. So our strategy is we need to reduce the temperature and decrease the temperature and use the suitable catalyst. We will get this kind of graph, which is when the use high temperature, the production of BA will higher than the HMBA. But when we use the lower temperature, the production of HMBA is higher than BA. So we need to decrease the temperature and use the suitable catalyst, which is PDC.
Task 4. The sizing of the reactor. First, these are the assumptions made in calculating, and also these are the information gathered from the journal and other resources. So first is the calculation of the molar flow rate of 4-CBA, which is equals to the composition of CBA in the inlet times with the molar flow rate of the crude terephthalic acid divided by the molecular weight of the 4-CBA, which will give me 68.38 mole per hour. Next is the volumetric flow rate from FA0 equals to CA0 V0, and by assuming the value of CA0 to be 0.01 mole per dm cube, the volumetric flow rate that I get is 66,838 dm cube per hour. Next is the conversion, which is the amount of A reacted over the amount of A in feed. In the inlet, there are 3000 ppm of 4-CBA, and in the outlet, there are 25 ppm of 4-CBA, which means the reacted is the inlet minus outlet over the inlet, which equals to 0.99. The reaction occurs in first order kinetics in terms of 4-CBA, and it is in constant volume because it is in liquid phase, and hence the rate law is negative RA equals to KCA0 1 minus X. As for the rate constant, we found an experimental values for the rate constant, which there are 5 of them, from a journal, and we get the average value, which is 4.26 per minute, and after converting that into per hour, we get K equals to 255.6 per hour. So the reactor used is packed bed reactor, and the mole balance of the PBR is W equals to integration of dFA over RA prime. dFA also equals to negative FA not dx, and RA prime equals to RA over density of the catalyst. By substituting those, we will get W equals to integration of FA naught dx over KCA naught 1 minus X over rho, which is the density of the catalyst. After integrating that and substituting the values, the weight of the catalyst is calculated to be 1480.87 kilograms. The weight of the catalyst also equals to the density of the catalyst times with the volume of the reactor, and hence we can find the volume of the reactor, which is the weight of the catalyst divided by the density of the catalyst, which we find to be the volume is equals to 123.2 dm cube.
Now I'll explain about task 5, which is type of separation system used. We use evaporator and crystallizer. The function of evaporator is to remove a certain amount of water to increase the concentration of purified TA in the solution, while the function of crystallizer is to crystallize the purified TA so that the product will be in solid form. To remove the impurities, they are water soluble and hence will remain in the model liquor during the crystallization process.
Hello, so today I'll be talking about the evaporator part of this project. So the basic fundamental objective of evaporator is to increase the concentration of the solution by evaporating the water. So in this case, we have this diagram which symbolizes the evaporator in this process. So in this evaporator, we have XA, XB, XC, and XD, where XA is 4-CBA, XB is TA, XC is TBA, and XD is the water content. So in this evaporator, we see that there are amount of water that has been evaporated from this evaporator, and we also have the amount of energy supplied for the water to be evaporated. So the assumption that we made in this experiment is that the inlet concentration of 4-CBA is 15 ppm, and the outlet concentration of 4-CBA is 20 ppm. And we also assume that there is no heat loss in this evaporator, is fully insulated, and the density of the solution is 1 gram per milliliter. It is same as the water. And as well as we have the inlet and outlet temperature is 100 degrees Celsius. This is because when you have 100 degrees Celsius, we don't need extra energy to change the temperature to 100 degrees Celsius, and then only evaporate. So if you already set the temperature to 100 degrees Celsius, it only need latent heat energy for the water to evaporate. So the calculation is that we first assume that the inlet water, the inlet for CBA concentration is 15 ppm. So with this equation, we can find how many mass of the water is included inside the inlet, and also assuming there's a 20 ppm that is exiting the exit of the evaporator, we also can find the mass of water exiting the evaporator. So we can find the difference. The difference with the two mass of the water is the mass lost by the water, which is the mass evaporated. So to evaporate 15,158.33 kilogram of water, it requires around this much of energy. So this data, the Q here, we got from the steam table, which is the latent heat of energy of water to be evaporated at 100 degrees Celsius saturated. And also we can find that the percentage that is evaporated is 54.06. So that is more or less for the evaporated part. Thank you.
So crystallization is a technique used for the purification of substances, a separation technique to separate solids from a solution. So for this crystallization column, the temperature ranges between 90 to 110 degrees Celsius. And because of the reduction temperature, there is no water being evaporated. So here we have the box. In the feed comes in 4-CBA, terephthalic acid, PTA, and water. In the solution stream in the mother liquor goes out 4-CBA, TA, PTA, and water. The crystal stream goes out TA and also water. One information that we found in the literature review is that the solubility at 100 degrees Celsius is 75.5 of TA. So we did the 4-CBA balance. First, we had the feed and also the composition of 4-CBA in the feed, and the composition of the 4-CBA in the solution is given because the problem required us to find a concentration less than 25 ppm. So the mass flow rate for the mother liquor or solution is found. So first we did the total balance, having the mass flow rate of the feed and also the mass flow rate of the solution. We could find the mass flow rate of the crystals. Later on we did the PTA balance, relating the feed and also the solution stream. And later on we did also the water balance, relating the feed stream, the crystal stream, and the solution stream. And the value that we found was 0.4104. To find the composition of TA in the crystals is just 1 minus this 141, that is 0.59. And here we have a table with all of the values calculated.
Now I will talk about the task 7, which is strategy to maximize the production of purified TA in crystal form. As you can see in the diagram, the increasing in temperature will result the increasing in solubility of TA. So our strategy is decrease the temperature so that the solubility will decrease. So the amount of water, more fraction of water in solution will increase. When the amount of more fraction of water increase, the amount of water in crystal will decrease. So it will increase the amount of TA crystal in crystal stream. Now we will talk about the reflection throughout the integrated project. First, we learn how the reactor separator system work in industry. We learn how to find the data and information from the journal and many sources to make sure that our calculation and result is valid. Next, we learn how to choose the suitable reactor separator system for each process. So, as we learn in the lecture, we learn many types of reactor and separator system. So, based on the problem that given by the integrated project, we need to find the suitable reactor and separator system. to make sure that our result is valid. Next is choose the suitable catalyst based on the reaction. Throughout our integrated project, we find many types of the catalysts that used in industry for this reaction. So we learn how to choose the suitable catalyst so that the product meet the criteria that we want. Maximize the selectivity and yield of the desired product, and also maximize the production of the industrial product. So we learn how to find the factor that affecting the selectivity, yield, production of the product. So to make sure that we can maximize the selectivity and also to maximize the production. That's all from us.